the directory now, right?
I can access it, but I cannot copy from it somehow. I tried copying.
No, you cannot copy inside it because it's owned by Jakob, but you can copy from the directory to your home, for instance. You can copy it to your home. So you can read it, I guess.
Oh, we cannot see any screen.
Okay, let me share a screen. Yeah, suppose Jakob should come back soon. I mean, you have, so if we start again, you should be able to access this directory here.
Mm-hmm.
And you all can do ls and see the content of it. Right?
Yeah.
And if you want though to edit something you cannot, because like you learned yesterday, this directory is owned by Jakob, but you have only reading rights of it. So you cannot write something in it, but on the other hand, you can copy what is inside out. So this, for instance, if I want to copy these slides, I copy slides to my home, and then I can edit it. All right. Okay, let me try to contact Jakob, because at the moment, Stelios?
Yeah, there's a Wi-Fi issue at the institute. I fixed the Wi-Fi outside our building. I'll take him a dongle to see if he can connect with Ethernet. That should be fine.
Okay. Maybe we stop the recording at the moment anyway. It's let's see.
Okay, now you get rid of Simone's rights. Or
no, I just stopped sharing.
Okay.
Start sharing, Jakob. It's
okay.
Fine.
Stop. Okay. Yeah. Sorry. I hope that doesn't happen again. Yeah. So the address is like what you already said. I mean, so in this case, I connect with this command to the machine, and then if you want to copy, secure copy, then the command is scp. Recursively, you put in -r if you want to copy a folder structure, and then the parse in principle is given by a double point, and then the path to the directory. So you take this one here, and you put it here. Okay, this is, and then you have to put the location, the other location where you want. I mean, this is the source, and then you need to add the destination at the end. So if you make a double point, this will be copied to this directory where you are in the moment. Okay, let's go back to the slides. So I think I was still on the first page as a connection was lost. I just was mentioning on which sources this course is based on, and I was giving you some. I mean, in general, these 2 pages, the Center of Excellence POP, which is focusing on, on optimization and profiling of HPC application. This might be interesting for you to take a look to this page. They have a lot of tutorials and training materials there, and also especially with a focus on profiling and of your HPC applications. But also we will have a training event in April. We have a session on this. And in general, it might be also interesting for you to take a look to the training website of Praise. Nowadays, if everything is online, I mean, there on this page is there's in principle an announcement of all the European training events which are for HPC, which might be specialized. So maybe you find also a special training event for your field there. Okay, but today we will just talk a basic introduction to OpenMP. Okay, so a reminder of parallel strategies. We had already a course by Simone on Monday on this. So here we will talk about multi-threaded shared memory parallelization. We use multiple threads that share the common memory address. So here's a sketch from the source. So you have a master thread which starts a program, and then you have start a parallel region where this spreads out. You start multiple threads which are running on different cores. Then so you have a parallel region, and after you which have shared memory, and after you run through this parallel region, you close it again, or the program close it again, and then you have again one the master thread which is running, and until you end up at the next parallel region. And all the threads have access to the same memory. This means you can only parallelize within a node. So which, I mean, the memory inside the node, the memory address inside the node is in principle shared. So if you want to run on two nodes, then you need other protocols or other parallelization methods to do so. So, for example, MPI would be one of these methods. So you there you have to think about how to exchange data between processes. Sorry, I just closed the door. It's okay, so we will, in principle, today learn how to use more than one core on one board. So just a reminder, I mean, yesterday, George already introduced you to this. What is the environment on Cyclone? So Cyclone consists of 17 CPU nodes, which are equipped with Intel Xeon processors. I think it's Cascades Lake. Each node has 40 cores. And then there are 16 GPU nodes, each equipped with 4 NVIDIA Volta GPUs. If you want to learn a bit more about what kind of CPUs are there and how many processors are available, you can use this command. So if you be on the machine, for example, on the head node, I think I'm not anymore there. You can do this, and then you see the processors, and for example, yeah, 40, where you see also the physical ID and so on. Okay, so if you, I mean, this is useful if you be on a new machine and you want to understand how many how efficient you can run on this machine, and how many threads you can use, and so on. Okay, so today most of the session we will just use a default GNU compiler, which you can take a look to which version this is by just using EuroCC version. You see it's 4.8. Later we will use, at the end of the session, we will use the module system to use newer versions of EuroCC, or even the Intel compiler. Okay, so again, a reminder, so we need to edit files. Yesterday, I think you were introduced to Nano. I'm usually using Vim on the machine to edit files. So I just wanted to show you the basic commands that you're able to edit files. For example, you can open a file with this command Vim and then the file name. And usually you can switch using the keyboard button insert between insert and replace mode. So let's do it. So Vim example .text, for example. So this is an empty file if it doesn't exist, and then you can switch between. You see below in principle. Now it's insert, so now you can write something in the file. For example, example, and then you can write this file and access this file if you use Control C. Then you enter this command line. And then with a double point, you can exit it with quit, or you can write it and exit this with write and exit. So this needs to be used to edit the submit scripts and the program files to add the OpenMP commands. Okay, so I just now write and quit, and on the slides part 1, if you got them, I think the slides is included that you can use it. You can take a look later if you forgot it. Then there are the Slurm. I mean, the queuing system of the system is Slurm. So usually, if you write a submit script, you can submit this. This job by using sbatch, the command sbatch. Later, in the example, I have the commands again, so you will see it later. So we don't have to go it in detail. I just wanted to, if you show it here already, so you can take a look to if your job is running by sq-u user. Okay, if the machines. If there are not so many jobs running, you don't need this -u user, because if you just use SQ, you see all the jobs which are running. But if you want to see only your jobs, then you can have this option -u and then your user ID. If you accidentally submit something which is running for ages and you or it's running or it's producing errors or whatever, you can cancel your job with cancel your job ID. Yeah, I think this is not needed today, but in general, if you have a preparatory access and you want to do some scaling or so, and you recognize your program is not scaling well, this is the command to remember. Okay, so let's start with OpenMP. Why OpenMP? OpenMP can parallelize programs. And this can run on your workstation or on a node on a cluster. So actually all workstation nowadays have a multi-core architecture. So if you have a program, it's even speed up your program on your local PC or even on your laptop. It's quite straightforward. So it enables parallelizing one part of the program without rebuilding your software. So you get speed up with a limited time of investment into programming. However, clear if you want to have a sufficient efficient parallelization, you need also to invest a lot of time at the end of the day. But the first steps are quite straightforward. Moreover, you can easily the serial and the OpenMP version can exist between next to each other. So if you don't add the compiler flag, you don't use API library functions. You can also compile the serial code. And you can use it for a hybrid programming scheme. So if you have a program which is parallelized with API, usually, so how we are, for example, using it, we using OpenMP to fill up the whole node. So if you run on, let's say, 10 nodes, then we run on each node one MPI task, and then on each node 40 OpenMP threads, so we can efficiently use all available computing power. Okay, OpenMPI is a multi-threaded shared memory parallelization. Use multiple threads that share a common memory address. We already said this. Fortran and C is supported. It's pragma based, so it's used directives than function, but it's also an API, so it contains also simple functionalities, which we will see. Okay, so in principle, how this looks like, we have three components of OpenMP. We have the compiler directive, and then language extension for shared memory parallelization. So we have, and in principle, the syntax looks like this. So we have the directive, then we have the construct, and then we have clauses, which where we can, for example, here's an example for C. So pragma is a directive for the compiler, then the construct is OpenMP parallel. So this opens a parallel region. And then we have clauses that, for example, this data should be shared. So the runtime libraries in interlib, OpenMP5, and for GNU-lib, yeah, this one here. And on top of this, there are environment variables which you can use to how the program is. I mean, if you want to run 5 threads, then there's a environment variable which is called OMP_num_threads, where you can tell, in principle, the machine how many threads you want to use. There are more, but this is maybe needed if you really have a hybrid program, or if you, for example, run on the GPU node and you have code which is partly running also on the CPUs. There are environment variables how you can pin, for example, your threads to that they are as close as possible to the GPUs. But this is point. Okay, so let's start with the introduction. So here's a simple sketch of this. So you start, in principle, here on the right side, you have this this code. You start with a single thread. If you enter this function, then you define, as we already said, this parallel region with hash and pragma, and then you say, okay, you have a parallel region which you indicate as OMP parallel. Then everything which is inside this brackets is then parallel. So you can put here a work which can be done parallel, and then if this is closed here, you enter again the single region. So it's a so-called fork join concept. So you fork here from your single from your master threads to the parallel region. So you open all the threads as we saw in the picture before, and then here you close it again. So there are some constraints. Clearly, you're not allowed to jump in or out into parallel regions in the middle, or you cannot. I mean, if you the if else block has to be inside the parallel, so you cannot have an else, an if inside and else outside, and so on. and a thread can terminate the program in the block. In general, the OpenMP runtime takes care of the thread managing, how the threads are forked and how they are joined. And as I already mentioned, you can specify the number of threads via the environment variable open this one, which we will see extensively in the next couple of hours. Okay, so then, as I said, the OpenMP library contains also some function which one can use within the parallel region, which is which we will use also here. So some information how many number of threads are existing, and what are the ID of the this is here with this function you get the ID number of the thread which is asking for it, and with this function you get the total number of threads which are running within the parallel region. For this, you have to include the header file of OpenMP. Okay, so how to? Okay, so you put this pragmas into your code. So how you compile then the code? Via the new compiler, you have to just simply add the flag -f OpenMP to your compile line. So without it, it will not compile for OpenMP. With it, it will look for this pragmas OpenMP and will enable the multi-threaded version. This is if you use intro compiler, you need a Q here instead of an F. In principle, it might be that if you forget it, probably your compiler will just run through, but you will recognize afterwards it's not parallelized. And then, for example, on your local resources, if there's a question, just are there questions? Because I hear something. Okay. So on your local resources, for example, you can, you use this environment variable to tell the machine how many threads you want to have, so you can export this before you start the program. And then, you export this. For example, here you want to have 10 number threads, and then you just start the program. And then, if the program contains a parallel region, it will use 10 threads. Or you don't need to export it; you can just write it in front of your starting of the program. On Cyclone, we will do this via submit script. So we will put this line then into the submit script. So if you want to have 10 threads, we can put this into the submit script. So later, for the first exercise, we will take a look to the submit script, and then when it looks a bit like this. Okay, let's do the first one.
Can you comment on the option tasks per node and how that relates to the number of threads?
Mm-hmm.
In the previous slide.
Yes. This one, yeah. In principle, you can also go now to the yes. So in principle, you can and task per node. I think this is a remainder of an MPI program. So you ask 10 resources for 10 tasks.
Like Jakob said, that one is for the number of processes you want to use. So usually it's used for MPI. But if you want to specify the number of cores, there is another flag that is cores per task, something like that. But like Jakob is doing, the important is OpenMP number of threads. So that one should be.
Yes, I just recognize it now. Yeah. So this is a reminder of the number of in the number of processes in an MPI environment it's called task, or each of these processes is a task. And then in case of OpenMP, you have threads. So yeah, I think there's another Slurm environment, a Slurm variable for number of threads or number of cores which you want. Yes.
Anyway, that line can be omitted if we only do OpenMP.
Sorry?
So we could omit that line if we're doing OpenMP.
Yes.
Okay, thanks.
It's also a bit, yeah, it's sometimes, so if you have a hybrid prioritization, then it's sometimes important how to, that you allocate the resources which you need. So for example, you want to make sure that you have enough cores available for all the threads. If you don't do this, I mean, Slurm provides you, Slurm can provide you, I mean, you can use Slurm for getting these resources. If you make a, I mean, if you don't ask for enough resources, can happen that you end up with on a smaller number of core partition, and then the threads and the tasks are not correctly pinned to your pinned to the CPU, and then your program is slower. But I think this is yeah. Okay, let's just take the first exercise. So just make a folder. I called it here TOMP, and copy the first exercise into this folder. Yeah, let's do it.
Jakob?
Yes.
Has permission denied for me when I make the directory to Tom?
Okay. So you need to be, so you need to be in your home folder. So I'm not in my folder.
Ah, okay. Sorry.
And so you make just CD. So if you're in
yeah.
So if you'll be here, just make CD. Then just you can make the for example Tom1. I already did. And then hopefully you can access. I think. So if you mark something and then you use the middle mouse button, you copy this what you highlighted. So yes, Panel is right. So just enter the folder, and then we can take a look into the submit script. Yes. Yeah, I simply overlooked the end task per node. But as George already said, in the moment you each job anyway uses one node, so you cannot share nodes. So this option is anyway not needed. You can delete this. Okay, so in principle, the output of this program will be, I mean, the error output will be stored in x01.error. If I highlight this, is not really visible. And the output in .out. Okay, then here reported some slurms. Infos, and then here's just the start of the program. So if you go there, we can now write OMP number of threads equal, let's say 5. And then we can close it, or we can go to the command line with Control-C and then close it with double point and write, because we want to write it, and quit. What do you have on the slide? Yeah, let's take a look to the program here. So in the moment, it's just a program which is saying hi. And we can compile it by, can copy this. Not working. And using then sbatch submit x01.sh, and you see how to react to, I mean, now you don't need to recompile it every time, because if you compile it, you generate a binary file, which is called A in this case. So here, this marks your, I mean, this line, this A here marks how your program looks like, or how the, not how the name of the program is. You can program here. And this generates a binary file, which is called program, and then you can reuse this. I mean, it's existing, and then you can, if you start a new job, you can reuse it. Okay, so you see, in the meantime, I submitted this. In the meantime, I get this. I mean, it was running on the machine, and it was writing to this file. Let's take a look to this file. And actually, what we see here is that, I mean, you see the infos here, and here is actually the printout of the program. Just say hi, and then it's finished. So you might ask, we just wrote OpenMP number of threads equal to 5, and we just see 1 hi, so it's but okay. Actually, first of all, we didn't use we didn't use the compiler flag here, and in the program itself, there's no parallel region in the moment. So we have to add this. Let's take a look to the slides. Could everyone submit? Could everyone run this? Well, do someone has problems with running? Or with copying?
Jaco, can you please do the process from the beginning? It's because I'm a beginner, it was a bit too fast for me to follow.
Yes.
Sorry.
Yes. Okay. So did you copy the files? I mean, first of all, you need to copy the exercise into your folder. So did you do this? So you can.
I think so. Yeah.
So you copied it?
Okay, I'll be honest with you. Just one moment, I got completely lost, and now I'm experiencing a bit of chaos. So, is there any chance you can just do it straight from the beginning? I don't know, but if I'm gonna delay the training, I'd rather you maybe just send me some notes via email or whatever.
Yeah, I mean, at the end we will put the material on GitLab.
Okay.
On GitHub, sorry. So you can also, I mean, it's available there, so you can take a look there. And I mean, it's and if you got already the slides, it's basically really the steps which are maybe shown here. These are the basic steps in principle. So you copy your the directory to your, the files to your home directory where you can edit this. Okay, here this is just to take a look to the submit script. In principle, you can submit the submit script which you already, which is already existing here without editing it, but just for later. And then you, you need to compile the program, and then you can just use sbatch to submit the program.
Okay.
Yeah.
Yeah.
So I think Angelos was asking a question, if one can compile always on the front node, or if one uses submit script. Basically, this depends a bit on the machine environment. So and how heavy your compilation is. So if you just have a simple program like we have here, or if your compilation doesn't take too much resources, then you are able to do this on the front node. But if you really have heavy compilation, if you have a very big package which takes
well, sorry, George did say yesterday that we don't run anything on the head node, and ideally you shouldn't. Obviously, if it's something small, it's fine. But you should learn to do as much as possible via the queuing system, so that you learn how to use it for your future uses as well.
Yes, the problem is on the front node. If you run stuff on the front node, clear, you don't run anything on the front node, but if you, depends on how heavy the compilation is. Yeah, we will compile the programs which we have here in the exercise on the. You can also submit them. Which, ideally, you allocate a node for this, and then you do this. With slog, and you run it on the nodes, compile on the nodes. But if it's really fast, if it's a small program, then if you don't overload the front node with it, it might be possible. Okay. Okay, so let's. I think we can just let's add this. Let's open a parallel region in our program. So let's open the program and add this to our program. Like this. So in principle, this program just says print hi to the file we already saw this. So if you put this pragma OpenMP parallel in front, then we need to compile it. Where it is.
No need of brackets?
You don't need brackets in this case. If you have more than one command following this pragma, then you need brackets. In this case, fprintf is for should work. Let's test it. No, it doesn't work. So you need brackets. Yeah. Okay, so you need brackets. Let's see.
Jakob, you are compiled as program and not as A.
Ah,
So you're executing A and not.
thanks. Okay, I think
also without brackets was fine. Just you were running the old executable.
yeah, makes sense. Okay, yeah. Okay, so no, I was too fast. Or I don't know. So yes, so you need to compile it with. I mean, you need to add the flag, otherwise you will not see it. And you need also to name it correctly. Otherwise, you start the old program and you don't see that. You don't parallelize it, as I did. Yes. Okay. So yeah. So if you look now into the file, you see 5 highs because we just added in the submit script, and we just wrote we want to have 5 OpenMP threads. If you might ask if you don't have it, what happened then? Let's take a look. Okay, you see then in principle the default value is the number, of course. So you see in principle here, I think 40 highs. Let's check. Yeah, so there are 40 highs. Yeah, here. Then okay, so if you don't do it, then you see the default value. I'm not sure now. We have 5 minutes after. Let me take a look. What we still have. Maybe we can just go to the. I mean, just go to this slide. Add some environment variables. Some OpenMP functions, and then afterwards, before we go to data sharing, we make a small break. Okay, so we already in principle did this. So the number of threads can be defined before running. So, for example, you can look how it looks like if you do a for loop in your submit script. I mean, you had yesterday basic bash programming. So here just do a for loop where n is running from 1 to 10. And then I'm setting, I have an echo here where I say, okay, I will run this number of threads n, and then I execute it. And then I'm running over this number of threads. Because you might get 5 because I started with saying to write OMP underscore number of threads equal to 5 in front of .a. So maybe check the submit script. What actually is your execution command? Okay, let's take a look what this program is doing. So let's submit it and take a look to the output. And you see in this case, okay, here's echo, and then the program say hi, and then the echo the n is running to 2, and then we start with 2 threads, and so on until 10, I think. Yes. You see, number of threads are 10, and 10 of the threads say hello. Okay. And as Panos already said, basically you can oversubscribe a node, so you can open more threads than resources on the machine. So you could, for example, you can run. You can say I want to have 80 threads or 250. in some cases, you might see some speed up beyond the number of the resources which you have, but it's actually you cannot speed up as much as possible. I mean, basically only what the machine has. So let's do it like this. So I let now the for loop run from 52 to 250. And then I should see just more highs. Okay, I mean, I guess this is. Oh, I'm just maybe take a look to the submit script. So if you take a look to the submit script, submit. At the beginning, I said change right here OMP number threads equal to 5. And this is would give you 5 threads. So if you don't have this here, this the program just takes the default number, and the default number is the number of available cores, which is 40 in this case. So if you run it like this, you should see 40 highs. Okay, so yeah, now let's see how to use the OpenMP API. As I said, there are you can get some information about the ID of the threads and how many threads are running. For this, you have to include the header file. So if you do like this here, go back to the small program, include the header file. And maybe, yeah, here. So this function gives back an integer, this information about the IDs and the number of threads. And then you print them here out. So you say, okay, I write this and compile it again. Here. Okay, let's take a look again to the submit script that I have here. Okay, I just execute the default stuff. So let's take a look what happens if I submit it and run it. Yeah, you see that in principle all the 40 threads say hi, and they give yes, the 10th thread or the thread with ID 10 were the first one which printed out, and here's 0. Yes. And what you see is that this is really random like, so who comes serves first, so it doesn't mean that the first thread will be writing as the first one to the output script output file, which can cause this yeah, which can cause some bugs or some problems in your file animation. For the name. Okay, I will see it later. Okay. Yeah, I think this is. I think we can make a small break now. Maybe in 5 minutes we just start with other part, data sharing. I mean, I stay here, so if you have questions or remarks or whatever. So I think let's begin again at 17, 11, 18 maybe. It's about how to compile. I think if you compile on a node, the best thing is to use salloc. The problem is because of the number of participants. If everyone would reserve one node for themselves, then I mean, the cluster is too small for that. So due to that, we use here just submit scripts in dispatch. But so due to that, I wanted to avoid to show as alloc, just that not that everyone's trying it and then so the cluster is blocked. No. I mean, okay. I mean, you can just do as alloc and then minus capital N, which stands for node 1, and then okay, then there are additional options like the time. For example, if you wanted to have it, I'm not sure if you wanted to have it for. I think the first one is days, hours, and minutes. So, for example, if you want to have it for 1 minute, would be like this. And then you can also give partitions and reservations. So if you do this, then you have to wait until you get resources. If the cluster is full, this is not. I mean, the dispatch thing has the advantage that that you don't have to sit in front of your computer. Just make it remotely. But for compilation, you might run into very fast into issues, and then to have an interactive session, it's useful. And moreover, if you basically if you're the first time on a cluster, you might not exactly know how your program is runs, or you have problems with starting it. I mean, sometimes they use different commands and so on. Then it's very useful to have an interactive session really to try out the basics on the nodes. Sometimes the file system is different and so on. So you can catch quite a lot of beginner starting problems by having an active session open. But because we are we have so many participants in this training event, it's I think there are only 6 nodes reserved, and so only 6 could do in parallel stuff. So due to that, we use dispatch here. And you see now after 1 minute, my allocation is over, and I get pushed out of the node. When you see it here, this is about the name of the node. So I got computing node 14, and now I'm back on the front end. Okay, so let's go to back to the session again. So maybe just a reminder. We just had we just did the first exercise. Now we know how to compile this. One has to add this flag to the compiler to enable the parallelization with OpenMP. we learned how to run a simple program and how to ask for a specific number of threads, and that this header file, or that the library itself provides some functions which one can use to get some information about the thread number and the total number of threads. So as the next step would be, if we want to manipulate or if you want to work on data within a parallel region, we have to understand how we can interact with this data. Because if every thread is starting to access a specific memory or a specific data and works on it, then you might get a lot of mess. Okay, let's take a look. So for this, you have clauses. You can indicate, for example, private variables. So you write this at behind OpenMP parallel, or dependent where you behind the plug. I mean the end. So you can make a list of private variables which are private to each thread. You have to be careful. The initial value is undefined, and it's the variables are also undefined after you're leaving the parallel region. Then you can make a. You can also, I mean, you can indicate what kind of variables you want to share. To shared variables, all the threads, I mean, it's common to all threads, and all threads can write and read from it. In general, the variables are shared by default, so you don't have to indicate basically principle if you don't change the default value. So you can also say, okay, these variables should be private, and you need to make a list with the shared ones. Okay, let's take a look how this looks in the code itself. So for example, here you have two variables, two integers, one is a and one is b. And if you want to start here a parallel region, you want to say, okay, this variable a should be private. So you can write, okay, private, and then the list of the variables which are private, in this case just a, and b you want to be shared. So basically, what happens if your program enters this parallel region? Each of the threads get a copy of a, and as we already said before, this variable will be undefined, so it will not any will not have the value which you gave it before. Yeah, and the variable b is shared between the threads, and each thread can modify it, and all threads will see the same data. Yeah, as we said, you can also change the default value. Okay, let's go to the next exercise. Again, like we did before, we just copied the exercise 2 and go into the directory. And let's take a look to it. So this looks in principle like we end with exercise 1. We defined a variable which is called sum variable, assigned to 42, and then we have here a parallel region where we just get the number of threads and the ID number, and we print this out with the value of the variable. Yeah, so we can compile this via again the same command. Take a look to the submit script. Okay, it looks pretty the same like exercise 1. Let's do threads. Let's set it to 5 if we don't have a chaos. See here the output and the error is no name 2x02. Yeah, write it and quit it, and then I just submit it and see what the program is actually doing. Exercise out. So. Okay, so as before, it's print and thread 0 prints out. I mean, this is thread 0. Gives this is the ID of the thread, and that's the total number of threads, and the value of the variable. So it's shared by default. So everyone is giving 42 as the output. Yeah. So if you take a look, you see this. Now we want to try what happens if we manipulate this variable within a parallel region. So if we, for example, if we just assign the ID of the thread, and then we take a look what actually each thread is seeing here. Yeah, so let's change the code to do that. I think we are going over the time of this session now. Not sure if this is a problem or. I mean, I would continue it for a while and then move a bit the break a bit to later. I'm not sure if there are something against it or not. It's a bit difficult to see if the audience is not sitting in front of. Okay. Anyway, I edit this now. I compile it again, I guess. So let's see what happens if I submit it. What you actually see is that you get a racing condition. So I mean, you see what happens is that all the threads can access this variable. It's shared. So actually, what you see is if thread 1 is printing, thread 2 already changed it. So and so on. So actually, thread 2 is thread 3 and thread 2. Okay, so it happens that. So if you go back to the code, so you enter the parallel region. Each thread is changing it, and then it's printing out. And what happened here was that thread, I forgot which number of threads, but one of the threads was changing it, and as it was printing out, it was changed by another thread, so it printed out the other value. So the output is, you cannot really determine what kind of output you will have. So if you run it again, you will get something else. So what you can do is you can avoid this by by changing it to a private variable. So to avoid this race condition, you can just add private some variable in front. And then this is then this is private for each of the threads. Let's do it. Submit it. And there you see that now the variable is private for each of the threads, and sorry, there were some. I didn't. Did you say something or? Actually, Panos was asking a question, but I actually don't know the answer to it. So he asked, is there a type of variable that is not allowed to be used in these pragma directives?
Yeah, I don't know, Jakob, if you want, I can comment on it. I mean,
yeah, sure.
Like Panos is pointing out, this is a C programming, so it's not C++ at the moment, which means that you don't have classes, you don't have copy constructor, etc. So these are very basic variables that have a representation in memory, a direct representation in memory. So as far as it is an integer or a double number, etc., this will be copied. But if your variable is of a type pointer, what you're copying is only the pointer, which means that you will have two pointer types that are pointing to the same array, for instance. And so when you're trying to act, it's not copying the array, it's only
yeah. Yes, I think he also already he pointed out an example. So
yeah. So as far as it is integers, etc., it's fine. I don't know what happens with the static array. So if you define some variable like an array, a static array type, that's probably copied, because at that point it's the compiler knows that is an array, so it will copy the static array. It will create copies of the static array in a private way. But if it's a simple pointer, the compiler cannot know the size of the array, etc. We never copy it, we just copy the pointer value. I hope this is clear for who knows C. I know the argument pointers is always complicated, but for who knows C should be clear.
Yes, right.
Yeah.
Okay. Okay, so in principle, if we make it private, each thread has an own copy of it, and you see that then this copy is assigned to the ID of the thread, and you see in principle what you expect. Okay. So let's take a look what is actually the initial value of the private of each private variable. So you see we actually assign it to 42, and if you just add the ID number, we will see what is the initialization of this this variable. I just add it up. And you see that it's not 42 plus something, it's just the ID number, so which means it's initialized with the value 0. I mean, this would be the question here. What do you expect this code will produce? The private private variable is initialized with 0. You can also check what this first private is doing. Okay, then here's another example. So basically, the question here is, what do you expect the output of this program is showing? So we have this array is shared, and each thread writes his ID into the array, and then it's printed out, and then we check afterwards. I mean, we see what comes out here. And you need, because you're in this for loop, you initialize the integer I. You need to add standard C99 to your compiler flags that this program, like it is here, can compile. Are there other questions or other problems, or okay, let's just do this. Okay, I guess you could guess what happens. Each thread is writing to its own entry, the ID, and then the array is filled with the different thread IDs. So let's take a look. If we ask for more than 12 threads, maybe 20. yeah. This time it's probably in the error output. Yeah, we have a segmentation fault because the threads, which I mean, the array is just consists of 12 integer numbers, and if we run more than 12 threads, you want to access memory which you not ask for, and you get in segmentation fault. And in this case, you will see the error in the output file for the error. So if your program is not running, you might see some. I mean, here you see some information. Yeah, in principle, it's saying that you got a segmentation fault in line 15. Line 15. I guess. Yeah. Okay, he catched it here. Okay. Okay. Other questions? Okay, so I guess we can make we are a bit over the time, 50 minutes, maybe because of my disconnect. I guess we can make now a break for 15 minutes, and then we will start again at 12 o'clock with the next session on work sharing in principle, how we can parallelize for loops. Okay, so see you in 50. I mean, I'm still here, so you can, if you have questions or remarks or whatever, or problems with something not connected to the cluster, or then yeah, feel free to ask them. And not, then let's yeah, start again at 12 o'clock. Okay, just a reminder. I mean, we have in principle a breakout room where you can switch to, and Simone will be there, or you just maybe have to raise your hand that you are there. Could help you with anything you have. I mean, can answer questions there or can help you if you have problems.
Yeah, you should see a symbol breakout rooms. Depends on the app that you have. I don't know if it's on the phone or from the browser. You should see somewhere the name breakout rooms, and you should be able to join. Though when you join the room, you are switching. You are going out from the main presentation. So you go to a place where you need to then to come back if you want to.
But yeah, the advantage is that you would be more or less alone with Simone there, so that you don't have to. I mean, it might be better to break the ice or whatever. I mean, if you.
Yeah, if you have any kind of question that, like before, if you want to the specific question that you think they're not relevant for everybody, but problems to compile or whatever, just come there and they can reply to you.
and at the beginning of the session, we basically have one breakout room where if you have a specific problem or a question which you don't want to raise here, you can go there, and Simone will be there, I guess, to help you. However, if you change the room, then you cannot follow the presentation anymore. So, but okay, I mean, yeah, I just wanted to mention it again. Okay, we just were discussing data sharing. You can use, you can define variables which are private for each thread, and variables which are shared, which every thread can change. And now we will go to work sharing. So in principle, one can split. I mean, this is basically the idea of it. One want to split up the work of the computation in the parallel region, and by doing so, one speed up the program, so the execution time of your application. There are still several constructs available in OpenMP to do this. Here we will just discuss the do construct and tasking later in the afternoon or after the noon break. Okay, so how this basically look like for loops. So in principle, you write in front of for loop this OMP4 to make to tell the compiler this for loop will be parallelized. And you can you can combine this with a parallel region by writing parallel and then for. So I'm sorry, my videos on the right side. So in C or C++, it would look like so like this. So you write in front of the for loop and pragma OMP parallel for, and then the for loop. In Fortran, the code would look like this. Just a note: the loop index is private by default, and the work sharing dynamics inside the for loop can be controlled with clauses like how the how you work on this for loop. So this is in principle the next slide. So basically, if you write this in front of the for loop, this for loop will be split up. The iteration will be split up to the different threads. Accordingly, how many threads are available. How this is done, there are clauses for this, basically by writing this behind this command. So there are different scheduling, how you split up the work in the for loop are available. So you can have a static where you just give the first 10 iterations to thread 1, or the first thread which arrives there, and so on. And there's in principle the option of dynamic to have dynamical scheduling and guided scheduling. So I think let's go to the examples. Okay, let's go to the loop construct. So in principle, you could, for a loop, this looks like this. So you can, if you open a parallel region and you have several for loops, you can write this this pragma in front of the for loop. If the parallel region is open, you only have to be careful if you manipulate if you work on shared data inside the for loop, then you create race conditions. Like, for example, if you sum up a variable and each of the threads are accessing this variable, you will probably get a random result at the end of the for loop. For this, you basically have, in this case, this can happen, for example, if you have reduction, so you want to sum up a bunch of variables. So if you think about, you have you want to sum up elements of an array. And if you do this within a for loop, and you parallelize this for loop, so you can split up the for loop as you can split up the summation in bunches. So you can say, okay, thread 1 sums up the first part of the summation. Thread 2 is summing up the second part, and so on. And then at the end of the for loop, you need to reduce. You need to sum up the results of thread 1 and thread 2, that you find the answer is the correct one. And OpenMP, that this is done, that the result is always the same or correct. OpenMP provides the reduction clause. So this is the reduction clause looks like this. We have you write reduction, then the operator which you want to do, and then a list of the variables which you want to reduce. So this reduction is done on the scalar variables in the list. So how does it work? So each variable for each thread, a private reduction variable is created. So for example, here in our example, thread 1 would create a variable where all this the parts of the first part of the sum is sum up to, and thread 2 is doing the same, creates an own private variable where all the corresponding variables of the sum is summed up to, and then at the end of the loop, these two private variables will be summed up to get S back. So after the for loop, when the for loop is closed. So in the code itself, it would look like this. So before you can write after the OMP parallel 4, you just write this reduction clause. Reduction, you want to sum up this sum variable if it looks like this. So if you don't do this, you will get you will get a random result, or not a random, but you create a race condition if you want to avoid this, you can use this reduction clauses. There are basically different operators available for doing this. Here are some plus minus multiplication where the different I think there's a typo where the private variable are initiated by this. Okay, let's go to the let's do this on the cluster. Let's go to an exercise, because to see how this looks on the machine. Let's copy exercise 3 to your working directory. Let's do this. yeah, let's take a look how this the file looks like. So basically, you have here this operation. Yeah, we create we create two arrays of size n, which we take as an input. So here we create the array x and the array y, and then these two arrays will be filled with random number, which is down here. So basically, this is calling a malloc function to generate this number of doubles, and then we fill up this with random numbers, and then our actually computation, which we want to parallelize, is done here in the for loop. So we run over the arrays, we multiply array 1 x with a scalar, and then we sum this up to a final array, and we can take this here as serial code, and then we can try to parallelize the second loop. And at the end of this file, we will just compare. I mean, here is a comparison if z0 is equal to z1, and then here's a printout, which is checking, which is printing out the time which is needed for the different for loops, and if really both results are the same. Okay, let's go back. So let's compile this this piece of code. Okay, I think submit. Let's take a look to the submit script. You see, in principle, that this program is expecting some integer, so which contains information how long the array is. So in this case, it's a multiple of 2 to the power, yeah, something. To the power 13, 14, like this, I guess. Okay, so if we execute this, if we submit this, we get following a message. As we already discussed, as I tried to discuss, going through the code, you see the time spent in the first loop is 0.12 seconds in the second loop, because it's basically the same number of time, and the difference, both norms are, I mean, both resulting arrays are identical. Okay, now we can try to parallelize this by using OpenMP. Basically, by just writing in front of the second for loop this command. So we just tell the compiler that the next for loop is a parallel region, and you should split up the work. Yeah, it's useful to report the total number of threads. For the final, let's add this to the code. If you make a for if we make a for loop over the number of threads, that we see how the speed up is. Let's add this here. Just to have to see how OpenMP can speed up the second for loop. Hopefully the library is included. If not, we see this error. So we have to include the library. ARG should. This is on the slide run. No? Okay, what we have number of threads and th. Let's see what's coming out. Okay, so we didn't, I mean, if you remember in the, I mean, sorry, I'm jumping between files, it's maybe not the best thing, but you see we didn't really tell here how many threads we want to have, so it takes the default value, which is 40, and then in the output, if I submit this, in the output I see again the time spent for the first loop, time spent for the second loop, and you see that there's now a speed up by 1 magnitude, so by a factor of 10. So if you use 40 threads, we speeded up the for loop by a factor of 10. So we can now scan how this depends on the number of threads by just doing a for loop there. So let's go back to the slides. Yeah. Okay. Yes, unfortunately the browser gets updated. Yeah, I think the PDF version is I'm not sure if the PDF version is in the right format at the moment. No, it's part 1, introduction. Okay, here's the PDF version. I don't want to. There we are. So yeah, the question is, how does the runtime scale if we do a scan in principle? Now, let me maximize this. So we can just do we just put into our submit script a for loop. Let's do this here. 1, 2, 5, 10, 20, 42 threads equal to n done. Okay, let's see what happens. You see the program was running, so I mean it was still running, so the output was not the complete output was in the file, so it was printing it still. So what you see here, in principle, okay, if you start with one thread, you don't have parallelization. You see in principle that both for loops have the same execution time, and then if you do two threads, you have you divide this number by, it's not perfect, but it's almost a factor 2, going to 5, and so on. And then you see at some point there's just simply not enough work. You get some overheads from opening the OpenMP region. So you need to increase the number. I mean, you need to increase your number of computation to see further speed up. So you see at around here with 10 threads, you're almost at the minimum. And then even it happens if you oversubscribe. I mean, if there's not enough work anymore to do, it takes too much time to open the region and close it, then we need to speed up the computation. So if you, for example, increase the number of, I mean, if you increase your computations, say by just increasing the length of your array, and here factor 4 larger, then you should see some better scaling. Yeah, it takes longer. You see almost, I mean, from going from 1 to 2, you see that the execution time. Yeah, you see now a speed up going from 10 to 20 threads, but from 20 to 40 threads, you still not see the speed up. So speed up. So you need to have more work to do that you really can use of all the 40 cores efficiently. Okay. Okay, here's just the output of what we saw. So let's go to another example where, I mean, we didn't really use here the reduction clause because we didn't have really each thread had worked on its own data. But if we, for example, want to calculate a dot product, yeah, the sum of this, I mean, we need to sum up all the elements of this product. So if we parallelize this, we need to reduce it to one final value. So okay, for this there are the exercise 4 slides. So let's copy them. Let's take a look to it, what it's actually inside. Again, it takes a number from the command line, how long the array is. Then it creates this arrays with the size n and fills it up with random numbers. And then we have here the dot product. again, 2 loops to cross-check. So here we can we have a serial version of the for loop if you want, and then we have a parallelized version if we add the pragmas there, and then we have a cross-check here if both, I mean, if both norms are the same. Okay, let's copy it. Let's run it and see what comes out. Yeah, you see that the execution time is here from the first loop, from the second loop, and the different norms. And you see that the norms are the same. Okay, let's parallelize it using the second main loop. Or compile it. Submit it, and let's take a look at the output. Did I do something wrong? Ah. What I oh, it's there now. Okay, I don't really get it, but okay, let's write OMP number of threads here. Maybe there's a protection anyway. I mean, I just wanted to show that it's wrong, but seems to work. Let's put the reduction here. I mean, if you want to reduce the norm 1. Okay, I don't know somehow. Did someone catch what? I don't know why. What happened now?
Jakob, maybe you're not compiling with OpenMP. Just that.
Oh.
So you're they're ignored.
Okay. I don't know. This is. Yeah, so you should always add the compiler flags in front of OpenMP to the compiler. Otherwise, he ignores you and he don't give you any warning. So maybe it's a good example. Okay, let's do it again. Yeah. I copied them. Simon, thanks for spotting it. Okay, so what I did now, I add the flag, but I get rid of the reduction, and what you see is, okay, you actually didn't speed it up, and your result is also wrong. So you need to add the reduction clause there to really get the right result. So you want to sum it up, and then the name of the variable which you want to sum up, it's now 1. Yeah, compile it and run it. Let's take a look. The result is correct. Now the result is correct, and also the time of the execution got some speed up. So we can again scan how good are the speed up of our parameterization here by putting a for loop in our submit script. Yeah, let's do it again. 40. Do. And no. Well, how we know if this is a critical, I mean, if what's called, yeah, how we know if this needs to speed up or not. In principle, there are profiler tools to profile the whole application and to see which is then timing each function. I mentioned at the beginning of there's this Center of Excellence, which is called POP, which has some tutorials on these profilers. I mean, it would be my first step would go to there to take a look if you're interested to profile your application. And then clear, you only the first thing which the function which takes most of the time makes sense only to start optimizing this function, because this will essentially speed up your program. I mean, if the program is simple like this, then it's obvious that your computation are done in this for loop, and maybe the first step would be to look where actually your computations are done, and if you can identify for loops, then you can just add this in front, and then you see how good speed up is. But clearly, before you start to parallelize, it makes sense to understand which region of your code is actually your computational intensive part, and then to focus on this, because this will only if you parallelize this part, it will speed up your application. Maybe okay. We mentioned it several times, but I mean, we also at the next training event in April, we go a bit more in detail in this direction: optimization, profiling, and so on. Okay, this we had no. Yes, so in principle, this was what I wanted to show you about the parallelization or the work sharing using for loops. The next session will be on tasking, and this will be after the lunch break. So I guess we are a bit over the time, but I think almost good in time for the afternoon. I mean, for the lunch break. Yeah, the lunch in the afternoon session, we will discuss a bit tasking and how OpenMP can tell the compiler to auto-vectorize. Yeah, I think I'm still here, I guess, over the lunch break. So if you have questions, just raise your voice. I think yeah, and otherwise. See you, and I would say
we should start on schedule. So lunch break will be 10 minutes less. So let's start at 1:30 as scheduled, so we can finish on time at 3. So if everybody can be online again at 1:30, then Jakob can carry on with the next session, please. Okay.
Okay.